to say that I'm really grateful to the organizers of this conference that they decided to pronounce me an expert in functional programming. I have a question to all of you. Do you have any experience with functional programming? No? Nobody? I see no hands. So maybe, oh, there are some hands now. Maybe instead of using hands, we could just clap, because it records better on video. Is that all right with you, or is that a bad idea? Clap if you agree. Okay. Okay. Thank you. So, and of course, at any stage of this presentation, feel free to interrupt me somehow. I don't know, either raise your hand or shout really loudly, and there's a chance that I will hear you. My name is Maciej Godek. I am a sort of a software philosopher, and I'm going to debunk some myths about functional programming. I want to drag you into this beautiful, in my opinion, beautiful world of functional programming, and I'm going to warn you about some of the common confusions that people have when they try to approach functional programming. So the goal of this talk is to first is to explain what functional programming is. Second is to, as I said, to expose some common confusion, also to debunk some myths, show the value on some real examples of applicability of functional programming, and show some fallacies that arise when you don't use functional programming in your code. So if you're not sticking to the principles of functional programming. Can I please ask you to clap if you know how to program at all? Okay, that's good, because there will be some code presented here. The first myth that I'm going to debunk is that functional programming isn't well defined. I've heard it a number of times. If we go to Wikipedia, we read that functional programming is a programming paradigm that treats computation as the evaluation of mathematical functions and avoids changing state and mutable data. This is completely non-controversial definition, and it's valid. And the keyword here for us to focus on is the mathematical functions, or functions. The name functional programming originated from the idea that you can program in functions, but this is the source of the first confusion that can be made, namely that many programming languages such as C or JavaScript use the word function to denote a procedure, or to refer to a procedure, where procedure is a sequence of instructions that show how to achieve some result, such as to prepare or make something. This is also a quote from the Wikipedia. And here's an example procedure. Is there anybody who has trouble understanding this code, what it does? Well, if there's anybody, clap your hands. Yes, it is a procedure that tells the computer to print some message on some stream, and then it returns some basically useless value to the system where it was called from. And on the other hand, and here's an example, another more real-world example of a procedure for making, or two procedures actually, for making an instant soup. The first is pour in boiling water, put cover on and leave to sit for 3 minutes, and the good tasted instant noodle soup is now ready to serve. This is the sort of procedural thinking, and for a very long time we have been taught to program in this particular way, by instructing computers step by step what it is supposed to do. And function, in functional programming, function in mathematical sense is a relation that associates input to a single output according to some rule. So, for example, you can also use the C programming language to express a function square that takes some number and associates with some other number. For example, it associates 2 with 4, 3 with 9, and so on. And we can see from this example that we can use procedures from the C language to implement functions. And sometimes, because the word function is often used by by languages such as C or JavaScript to refer to a procedure, they use the term pure function to refer to a function in mathematical sense. Here are a few examples of functions from the standard C library. I don't know if you're familiar with C, but on the left we see things that actually are pure functions, like toLower, which takes a character and returns a lowercase character, or isDigit, that returns a Boolean value depending on whether the character on the input is a digit, and so on. The procedures, on the other hand, that are not functions are things like print or scanf or memcpy or clock, which returns the number of ticks that elapsed since the program started to run. And the procedure rund, which each time returns a different number, some random number. And on the left-hand side, there are operators that are functional in the sense that they denote some mathematical operations. And on the right-hand side, there are some operators like incrementation and decrementation and assignment in several flavors that these are not functional. These operate basically having something that functional programmers call side effect, that they change the state of some program. Another common myth is that functional programming is about using lambdas or closures or higher order functions. And well, lambda is a really funny name. If we check it on Wikipedia, you find that it's the 11th letter of the Greek alphabet, so that's not really helpful. Of course, the name originated from the lambda calculus, which is one of the theoretical models of computation that is considered in computer science. And the funny history with lambda is it started with a very important book, Principia Mathematica by Bertrand Russell and Alfred North Whitehead, where they used this circumflex or the roof symbol above the letter in function argument to differentiate between the value of a function at a point and the value of and the function meant as an object itself. So and here's another example of code that is not functional. It uses the word function. This is in JavaScript, and JavaScript uses the word function to denote a procedure, anonymous procedure. And this example creates a procedure which increases its internal counter each time it is called. So even though there are functions and closures in this code, this is not functional code. Is that clear to everyone, or should I don't know, explain it better? Yes? If that's unclear to someone, clap your hands? No? So if that's clear to everyone, clap your hands? Okay, thank you. So another myth is that objects are like nouns and functions are like verbs. Actually, in functional programming, you don't have any verbs. Verbs make sense, indeed, when we're referring to procedures, but they make no sense when you're referring to functions in mathematical sense. And here's an example in Haskell. This is a function which is called insertions. Insertions is a noun in English language, and it produces, I'm not going to get too deep into that function, but it produces, given an element and a list, it produces a set of all possible insertions of this element into that list, as you can see on this example usage. I hope that is clear. If it's not, clap your hands. And some other nouns that can be given as examples of pretty decent function names are power set or permutations or sorted. Sorted actually is a verb, but it is a participle, and this is the only way we can put this verb-like interpretation to functional programming. But it is more like a noun or like an adjective a little bit. So another myth is that pure functions cannot be implemented in non-functional or imperative or procedural way. And here are two examples of the factorial function. The one on the left is stateful. It instructs computer how to do things step by step. And the second one is purely functional. There is no notion of execution flow in there. I mean, in programming languages that are more targeted for functional programming, you usually don't have this return keyword, because it actually does two things. It breaks the current execution flow, and it makes the current procedure return or have some value. Return the value to the caller. And since in functional programming you usually assume that that the program is just an expression, there is no notion of execution flow whatsoever. And well, there is also, among people who are familiar with functional programming, I sometimes hear the myth that you need to understand category theory and things like monads in order to use functional programming. And the fact is that the core, this is actually this is the most important slide of this presentation, in that it describes the essence in functional programming. Imperative programs explain how to do things or perform actions, while functional programs mean things or refer to some objects. And this should be clear when I show you this example. So we're given a task of computing the sum of squares of initial 7 prime numbers. So if we try to approach procedurally to this problem, we would end up with something like this. We have a variable counter that we initialize to 7. We have a variable number, which will be the number that we are currently testing, and we initialize it to 0. And we have a variable sum that will contain the result of the thing that we are looking for. And while counter is greater than 0, if number is prime, then we increase sum by that number squared, and we decrease counter by 1 because we found this number. And regardless of whether the number is prime or not prime, we increase the number to test the next one. So we're testing number after number. Is this program clear to everyone? It's not in any real programming language. I just made it up, but it should be. It resembles Python. The important thing is that I have to explain to you, in addition to explaining the program itself, I have to tell you that the sum variable contains the thing that we are looking for. And in functional programs, I don't have to make such an explanation. So this is how the program would look like. It is sum map square over initial 7 only prime numbers. Of course, and this is actually, if we have these symbols like only prime numbers, initial, square map, and so on, if they are defined, then this is our program. If they are not, and we can see that it is a single expression, and it is like translation of the formulation of the problem to one-to-one to our programming language, to some functional programming language. Of course, sometimes we need to explain what these things like numbers or only or initial mean. So I will do that for you. We can define numbers as a sequence consisting of numbers from 0, where by numbers from n we understand a sequence which first element is n, and the other elements are the sequence numbers from n plus 1. I don't know if that's clear for you, or probably not. Should I explain something better? Clap your hands. Yeah, I've heard one clap. The thing in here, maybe, the second line in this definition, this apostrophe, parentheses, comma, or n, well, it says that we are building a sequence, and the first element of the sequence is the thing on the left of the dot, and the rest of the sequence is on the right of the dot. So on the left-hand side, we have an element, and on the right-hand side, we have some sequence. Maybe it will be clear if I show you some more examples. So if we have this function numbers from n, so this function will essentially, numbers from n will generate an infinite sequence consisting of 0, 1, 2, 3, 4, 5, 6, 7, and so on. And there will be infinitely many of these elements. And of course, we could ask how can we fit the infinite sequence into a finite memory of a computer, but that's a different question. In general, we can't, so we use some strategies like lazy evaluation, and we only produce this part of sequence that we actually try to refer to at the computation time. And here's how we understand only qualifying elements. If elements are an empty sequence, then only qualifying elements will also be an empty sequence. And if the elements we can decompose on the first element and the remaining elements, then we must check if the first element is qualifying, and if it is, we add it to the sequence, and if it is not, then we skip it. We just take only qualifying elements from the rest. Is this clear, or is this like very weird and spooky and difficult to understand? Is this weird? Clap your hands. Oh. I don't know, maybe next examples will show a bit more. Maybe, so let's, is this working? What we mean by initial n elements. If n is 0, if we want to take initial 0 elements, then this obviously will be an empty sequence. Is this clear? Or anyone wants to clap their hands? No. And otherwise, the sequence is non-empty, so it has its first element and it has some other elements. So we decompose these elements into the first and the rest, and we create a new sequence, and this time this will be a finite sequence that will consist of whose first element is the first element from the original sequence, and whose remaining elements are initial n-1 elements from the rest of the list. Is this clearer, or is this like some crazy shit? Is this weird? Clap your hands. Okay, I'm getting calmer. And now we may also explain what do we mean by a sum of a sequence of numbers, and if the numbers are, if the sequence is empty, then the sum of the elements is 0. We just say so. And if the sequence is non-empty, then we add the first element of the sequence to the sum of the rest of the sequence. Is this clear, or is this weird? Does it like, are you starting to feel a bit comfortable with this way of thinking? Clap your hands. No. Okay, three people, I think. So actually, I don't know how to understand this better because I'm a bit soaked into this way of thinking. But it's obvious, isn't it? Okay, and now, what is the true advantage? I hope that this time it will make it clearer, is what is called the substitution model of computation. That once we wrote this expression that really resembles the original formulation of the problem that we are trying to solve, we can analyze it or imagine the computation in terms of substitutions. For example, this bold number symbol here is our focus, and it can be replaced by the previous definition of a number with a sequence of elements, 0, 1, 2, 3, 4, 5, 6, and so on. Infinite sequence. I wrote 3 dots because I didn't have space to write indefinitely many elements. And if we now only take prime elements from this sequence, then we will have something like this. This will also be an infinite or infinite sequence, and we want to take only initial 7 elements from the sequence. So this will be that thing here, 2, 3, 5, 7, 11, 13, 19. And now we perform on each element of this list, we perform the square function. So we get a sequence 4, 9, 25, 49, 121, 169, 361. So is this clear, this reasoning? Is it beautiful? Clap your hands. Yeah, that's what I wanted to hear. So the only thing that's left is to add these numbers, and that's fairly simple. So another myth, or rather a misunderstanding, is that programmers, especially programmers with Python background, they often do not differentiate between binding and assignment. So it's understandable, because in Python you usually use this equal sign to do both of these things. If you have a variable that didn't exist before and you assign to it, so you use this equality sign. For example, you write x equals 0, then you define x to be 0. But if the variable existed before, then you assign this variable. And this distinction between binding and assignment is very important in functional programming, mainly because you don't use assignment in functional programming at all. And we have seen it actually on this example with the factorial, with the imperative version of factorial, where we had a variable that was updated in each step. I could go, no, I'm not going back there. So I think that this distinction between binding and assignment is easiest to see in Scheme, because you have three distinct forms that express each of these concepts. Definition creates a new binding in the current scope. So, like for example, you define x to be 5, and henceforth x will be 5 within the current scope. And this is the fact that this is current scope is important because it allows you to write functions that are values actually that refer to the same scope. So you implement recursion using this defined form. Assignment changes the value bound by a variable in the current scope. So if we defined some variable, we can change this value. But if the variable is unbound in some context, we cannot perform this set bank operator on it. And the third is probably the most commonly used, the operator that creates a new scope which might possibly shadow some existing binding. So we have this let form, let variable be some value, and within this parentheses, where are those three dots, each use of variable will refer to some value. But if we get out of this context, if the variable had been defined or bound to some other value, it will be bound to that value again. Is this clear? It might be confusing, but it's rather simple. It's just important to be able to differentiate between definition and assignment. And now we've seen in this definition from the Wikipedia that functional programming avoids mutable data. And I came up with this thought experiment. What are our options if we have some word in the language, for example, a word apple, and we would like the word apple to mean something else that it actually means. We don't want it to mean a fruit, but we would like, for example, to have it meaning a horse, for example. And how do we do that? How can we do this in the language? So I came up with two ideas. If anybody has some other, you can clap your hands or I don't know, come up here on stage. We could explain this new meaning, do what we just did. So we can say, oh, I've been riding an apple, and things like that. Have you seen this scene where this cowboy shot this other guy riding his apple? And now we understand what we mean, but we also know that all the previous occurrences of the word apple, they refer to a fruit. And now another way of changing the meaning of that word is to take a group of people and to conduct this crazy scientific experiment that I modify the internal representation of your brain so that you think that apple means horse, and you don't remember this situation. And the first situation corresponds to functional programming, and the second one it corresponds to the use of assignment in regular programming. And yes, it's that awkward if you try to perceive programs as expressions or as descriptions of some complex objects that you are interested in. So yeah, the problem with the second approach is that what would happen if I, for example, had a book that was about apples? Should it now refer to horses? And how do we make it refer to horses? That actually, that doesn't even make sense, which is why it is so difficult to explain. Okay, now I want to show you some problems that arise when we allow mutation or assignment in the language. Do you know these two operators, x plus equals y and x equals x plus y? Do you know what these mean? Do you agree that the right one is, the left one is the synonym for the right one, that they are the same? Clap your hands. Okay, do you disagree? Does anybody disagree? Clap your hands. Nobody disagrees. Okay, so let's check it. Probably you're right. Let's see. This is my poor man's version of Python interpreter. But actually, I wrote this in Python before moving it to slides, so it's not cheating. So let's assign or define x to be 5. Let's assign x to be x plus 3, and let's see what x is x. And we see that it is 8. So let's now assign 5. Let's do the same, but let's perform this plus equals operator. And now we see that we have the same results. You were probably right, but let's double check it just to be sure. So we assign 5 to x, then we assign x to y. We introduce another variable because we just want to make sure that these operations do not have any undesired effects on some other variables that we weren't tracking at that moment. So we introduce a new variable y, which gets the value of x. We assign x to be x plus 3, and we see that the value of x is now 8. And the value of y is still 5, as if it was at the moment of definition. I think that's reasonable. I mean, I'm calm to see this. When we do the same experiment with the plus y operator, we get the same results. So guess that I shouldn't have shown this to you because it was obvious. But let's triple check. Let's check it for arrays. Let's assign x to be an array 1 to 3. Let's assign y to be x, and let's assign x to be x plus 4, 5. And we see that x is now 1, 2, 3, 4, 5, and y is still 1, 2, 3, just as we would hope. I hope we would hope. Let's do the same with a plus equals operator, and we see that x is 1, 2, 3, 4, 5 as before, but y is also 1, 2, 3, 4, 5, which I don't know. Do you feel comfortable with that? Clap your hands. Yes, you feel comfortable, really, because what we could have made now, if this situation here isn't very dangerous, because I'm showing this to you. I'm showing you this. The x and y variables are both on the same slide. But if we had had this y variable initialized somewhere else, and we used this plus equals operator, then we would have a bug which is sometimes called spooky action at a distance. And besides, it proves that x plus equals y and x equals x plus y are not interchangeable. And so if you feel comfortable with that, but you didn't clap your hands before, then you're just a hypocrite. That's what I wanted to say. And let's see another example of problems that arise when we introduce mutability to our language. You know these default parameters in Python. We can say that x, we have a parameter x that has a default value of empty dictionary, and we return this empty dictionary. So we take the value of f. We see that it is an empty dictionary. Now we update this empty dictionary to have 5 under the key A. And now we invoke this f function once again. And it turns out that by altering the dictionary returned during the first invocation, we also modified this default value of this function. Do you feel comfortable with this? Clap your hands. Do you feel uncomfortable? Clap your hands. Yay. Yeah, that's good. Okay, so some other examples. It might be not obvious to you from the first moment, but the concepts of functional programming creep to other systems. Like, for example, there are Linux distributions such as Nix or Geeks that have this idea of functional package managers, which never modify the current state of your installation, of your system installation, but they only create a new state of your installation, and if you want, you can always go back to the old one. The same idea is with Git. When you are making a commit, Git is essentially immutable system that grows. You never, unless you are doing some weird things like force pushes. Git is immutable because it creates a new commit for each set of changes that you have in your repository. And as a matter of fact, also history itself, even though some politicians may try to reinterpret it, it's something that once it happens, you can't undo it. So some people argue that the world is imperative because, I don't know, I can take some object, I can break it, and I can't fix it. But actually, well, the world is functional in that we cannot change the current state. We just can go to a new state that has some, I don't know, some different values, so to speak. And another myth is that functional programming is a silver bullet and that it solves all the world's problems. Of course, it does not. For example, it's not a good use in systems programming, but it's very, very good in machine learning, I think, and also in, I don't know, in some mathematical processing and things like that. Also, there are some use cases that functional programming doesn't cover. For example, if you want to have a constraint systems, a system that preserves some constraints, you cannot express it in functional programs, in functional languages. But what you can do, and what functional programming is really good for, is to write a transformation of some language that, for example, is a constraint-based language or has some interesting semantics, and to transform it into imperative form. Because all the compilers, for example, or all the tools that interpret languages are actually functional in the sense that for the same input they should always, hopefully, return the same output. So to summarize this talk, programming languages or functional programming has the advantages that the code is easier to read and to refactor and is less prone to errors, and that it has no idea of the control flow. So for example, if you have some complex expression, you have the flexibility which arguments you want to use first. Also, you can evaluate it lazily, and because of this, it's probably the main reason why functional programming got so popular recently, is that you can easily parallelize code written in functional style, and we don't have to care what the computer will do. But it has some disadvantages, like, for example, it may cause performance penalties. It is difficult to reason about the resources that it uses. There is no, like, the theory for computational complexity is essentially a theory for procedural programming, and well, it does not apply as swiftly to functional programs, which can be transformed in many ways before they are evaluated. And it may lead to some awkward abstractions. I think, well, there are programmers who think that the cool thing about functional programming is that you can have some fixed point monadic type systems or whatever, some strange words from category theory, and they often get smug about this, but I don't think that this is the point of functional programming. This usually makes programs more difficult to understand. if you're using too much awkward abstraction in it. And the last disadvantage is that we don't know what the computer will do. So it's actually a two-sided sword. And that's it. Are there any questions?